In this video, we're going to discuss another physical property of space curves, which is curvature. In some sense, curvature is the three-dimensional analog of concavity. In Calculus 1, you looked at concavity of a curve, and you saw that the curve could either be bending upward or bending downward at any given point. In three-dimensional space, the curve can be bending in more directions than up or down. In fact, it could be bending in any particular direction. So we'd like a way to quantify how much the curve is bending or twisting at any particular time, at any particular point on the curve. And so that is going to be what the curvature represents. We can get an intuitive idea of how to define this if we just look at a particular curve in three-dimensional space. Right, so I'm just going to draw a curve here. Right, we can think of this as being in three-dimensional space. I'm not going to draw the axes, but it's just some curve that bends around in three-dimensional space. And what we can do is at each point, we know that we have a unit tangent vector. So I'm just going to, at each point, draw something that looks like a unit tangent vector. So remember, a unit tangent vector is length 1, and it points in the direction of the curve at that particular point. And so we have all of these unit tangent vectors, and so if we want to sort of measure how the curve is twisting around, or how it's curving around, what we can do is we could measure the rate at which the unit tangent vector turns per unit of length. Along that curve. So if I kind of looked like I did this, I spaced these tangent vectors out so that they look like they're about the same length apart on the curve. And so if I sort of look at that, if I look at how the tangent vectors are turning with respect to the length of the curve, then we get a quantity that measures how twisty this curve ends up being. All right, so the formal definition is really just putting this idea into formal mathematics. So we're going to define the curvature, which we'll denote by kappa of t. So the curvature kappa of a curve at any given point is the magnitude of the rate of change of the unit tangent vector with respect to the arc length parameter. So this is going to be our definition. So we're taking the unit tangent vector and we're measuring how it's changing. That's the magnitude of the rate of change. We're quantifying how much the curve is bending around at any given point. And the fact that it's with respect to the arc length parameter is this idea that we want to measure distance along the curve as opposed to in any given direction. This is one of these concepts that make most sense if we focus on distance along the curve, and this is one of the reasons why we developed the arc length parameter, was to handle just such an occasion. So we can summarize this whole definition in a simple equation. So this definition says that kappa is the magnitude of the rate of change of the unit tangent vector, so dt, with respect to the arc length parameter ds. Okay? And so usually this is the equation that we see. Right, so using this definition or using this equation, this would require us to take our function and to find the arc length parameter s, and then find the unit tangent vector and take the derivative and so on. However, it's possible and usually much easier if we find an alternative way to compute kappa as opposed to having to convert everything to the arc length parameter. Right, so the nice thing about this concept is to define it, we do need the arc length parameter, but we don't actually need to find s, the arc length parameter, to compute kappa. And so the way that the way that we can get around this is by looking at the following chain. So we know that kappa is the magnitude of dt over ds. That's our definition of curvature. Right? And like we've seen in a couple other, or at least one other instant, we can use the chain rule to think of this as dt dt, our given parameter, multiplied by dt ds. All right, so this is just the chain rule of differentiation. Right. Well, this first, the first quantity here in this product is just the derivative of the unit tangent vector t with respect to the parameter t. Okay. And dt ds we can think of as 1 over ds dt. I can just flip that around. And so this is equal to t prime of capital T times 1 over r prime of t. Right, so ds over dt is precisely r prime of t. We've seen that before. And so we can put this all back together. This is going to be the magnitude of t prime of t divided by the magnitude of r prime of t. Sorry, that should be r prime. Make sure that's clear. And so this formula here gives us a way of computing kappa at any given point t on the curve without having to find the arc length parameter s. All right, as we know, that can be difficult. And so this is a formula that allows us to compute the curvature with the given parameter t. So let's take a look at an example. So let's say we wanted to find the curvature of the curve given by the vector function r of t, 1 plus 2t, 3 plus 4t, and 5 plus 6t. Now, the first thing we should, in this case, notice about this particular curve is that this is the vector form of a line. And so we know the curve is a line, and we know that curvature is measuring sort of the twistiness of the curve. And the line is probably the least twisty curve I could ever imagine drawing. And so I would guess, just before we even start this, to make sure we understand this concept, our guess should be that the kappa value is going to equal 0, and this will be at any point t. Right? And this is what we are going to end up showing. But even before we begin, in this case, we can sort of see that we really should get 0 if kappa is measuring what we want it to measure. Right? And so we can go ahead and compute it using the formula that we just saw. So we do need to find r prime. So r prime here is a constant vector. It's 2, 4, 6 at the derivative of each of those expressions. So we get just a constant vector. And so the magnitude of r prime of t is just the square root of 2 squared plus 4 squared plus 6 squared, which is the square root of 56. All right, so I'll go ahead and record that for now. So now we need to compute the unit tangent vector, capital T. All right, well, we know this is r prime divided by the magnitude of r prime. And so this will be 1 over square root 56 times the vector 2, 4, 6. Okay. So now, once we have t, we can compute t prime by taking the derivative of this vector. Right? Well, notice that this vector is a constant vector. There's no t's. Right? Everything is a constant. And so the derivative vector for a constant vector is just the 0 vector. And so in this case, we know that kappa, and I'm going to write kappa of t because it technically kappa is a function of t. It's a function of the point on the curve, but of course this will it won't matter in this case because every point looks the same in terms of how much it is bending. So by the formula we just came up with, this is t prime of t divided by r prime of t and the magnitude of those vectors. Right? And so this is just the magnitude of t prime divided by the magnitude of r prime. And since t prime of t is equal to the 0 vector, this is just 0 over the square root of 56, which is 0. And so we get that this particular vector this particular curve has a curvature of 0 at every point t. Right? And so we could actually go back now. Instead of doing this particular line, you could go back and replace all of the constants, the 1, 2, 3, 4, 5, and 6, with just 6 arbitrary constants, a plus bt, c plus dt, e plus ft. And when you go through this process, we get basically the same exact thing. R prime will be a constant vector. Its magnitude will be whatever it is. It's just going to be a number. The tangent vector will be a constant vector so that t prime of t is 0. And so our curvature will be 0 over the magnitude of our derivative vector, which will always be 0. And so this example shows that the curvature of every line is equal to 0. In this example, we're going to look at the curvature of a circle. Now we can do this in a couple different ways, but what we're going to do is we're going to focus on a circle that's in the xy plane. And we're going to do one with arbitrary radius. So we want to find the curvature of the following curve. So r of t is going to equal a cosine of t, a sine of t, and 0. All right, so this is the vector form for a circle in the xy plane. It's in the xy plane because the z component is 0. And we know that a cosine t, a sine of t is a parametrization of a circle. It's the circle centered at the origin of radius a. And so we want to find the curvature of this. Now, before we begin, we kind of have some idea of what we should get. We should not get 0 here because a circle is curving. There is a curve to a circle. And we also should realize that the curvature is going to be the same at every point on the circle. And that's because regardless of what point on the circle you're at, the way the curve is bending is exactly the same as at every other point. And so we should get a constant here. And so if we go through and we just compute the curvature, so we need to compute r prime of t first. So r prime of t will be negative a sine of t, a cosine of t, and 0. The magnitude of this vector we're going to get a squared sine t squared plus a squared cosine t squared, of course, plus 0 squared. And when we do that, we can factor out the a squared, and we just get the square root of a squared, because sine squared plus cosine squared is 1. And so this is a. Remember a, I guess I didn't mention beginning a, we're thinking of as the radius of the circle, so a is positive in this case. So r prime of t, the magnitude of that is just a. And so our tangent vector t, we know is r prime of t divided by that magnitude of r prime of t that we just computed. And so it's going to be 1 over a times the vector r of t, r prime of t rather. And so we just get negative sine t, cosine t, and 0. All right, so we get rid of the a at each point there. All right, and now as we would expect, t prime, unlike the last example, is not 0. So we get negative cosine, negative sine, and 0. Okay. That magnitude we're going to get cosine squared of t plus sine squared of t. And of course, that's the square root of 1, which is 1. And so at the end of the day, we get that kappa at any point t is going to equal the magnitude of t prime divided by the magnitude of r prime. And we've seen these quantities are 1 and a respectively. So our curvature at any point t is a constant, as we would expect, and it's positive, which again we would expect, and the constant is 1 over a, where a is the radius of the circle. And so this really doesn't depend on the circle at all, it's just the radius. So what this tells us is that the larger the circle, the smaller the curvature. And this makes some physical sense. If you're thinking about walking in a circle, if you're walking in a circle with a small radius, you're feeling like you're turning quite a bit. But if you're walking in a really, really, really big circle, maybe a radius of a mile, something like that, you might not even realize that you're turning very much. And in particular, if you take a circle that's maybe 20 miles radius, you probably think you're walking in a straight line. And so the bigger that the circle is, the less that you are curving at any given time because of the size of that circle. Right? And so the principle here is that the larger circles have a smaller curvature. Of course, that means smaller circles have a larger curvature. But in any case, the curvature of any circle, not just one in the xy plane like that just made it easier to compute. But the curvature of any circle will always be 1 over the radius.